Hi, so today we're going to be going over a very common issue, which is when the ISL 6259 area is corroded and you have a battery that doesn't charge. So today's computer is a little bit unique compared to the regular ones that I get in because I just get this a little closer on the camera so you can see what I'm talking about. So this is the battery, right? See, these are wires coming out of the battery that are going to an electrical wall outlet. This is just, oh my god. Anyway, so let's move past that. Let's get this out of the machine and get started on the troubleshooting process. Psst. Check. Hello? Okay. No. Getting the board out of the machine should be something like a 90-second to 3-minute process if you have been doing it regularly. No reason to waste tons of time on the easy stuff. Now, one of the things you should do is not rip the microphone cable. It's one of my personal favorite things to do. I have probably wasted more money on microphones than the US government has wasted in the past 5 years. So, we're going to put this mess to the side. We're going to come back to that battery later. We're going to come back to that battery. I still got some words to give with that battery. So let's go over what's actually wrong with this thing. So one of the common things that you should do, one of the first things you should do is a physical inspection of the area of the board, and one of the things you're going to find very often is something like this. So this is the ISL 6259, and you got all these red probe pads here by the vias. You have some corroded looking vias, like right over here, that's a corroded pad, and you have some resistors that look like crap. So let's measure around the resistors that look like crap so I can explain to you what they actually do. So this is an 820-3115 board. Let's open that in the board view. Let's also not tell you where to get them because you should learn how to use Google if you are going to fix laptop motherboards. And get started. So first let's go over what a current sensing circuit does, because I'm theorizing that that's the problem. I haven't even started testing yet, but since I know I may get into testing and finding this as the fault later, I would like to at least give you an idea of what is going on here so that you're not totally lost. And of course, it is far too much to expect that my PDF reader will anti-alias anything, so I'm afraid you're just going to have to look at it jagged. Is what it is. Thank God bless open source software like Ocular. I'm sure it'll anti-alias as soon as the video's done. That's usually how this junk works. Alrighty, so this is the whole idea behind a current sensing circuit. So this all looks like confusing crap, but just let me simplify it. This is power that comes from the charger. It goes through these transistors, which will open based on the ISL6259 telling them to. So pretty much this chip, the ISL6259, one of its functions is to tell the charger when it can open and come through to this part of the machine. This is a current sensing circuit. The idea of a current sensing circuit is as follows. You have power, you have a resistor. This is a current sensing resistor. So it's a very, very small resistor. It's 0.02 ohms, which is not going to resist a lot of power. It's not going to make any actual difference in the operation of the circuit or the amount of power going to the circuit. There will be a very, very small drop in voltage from here to here. It's going to be very, very super small drop in voltage. Now, the drop in voltage is going to vary depending on how much current or amperage the actual computer is using. So this here is called a high side current sensing because this is happening before the system uses its power. So this is happening before this pretty much makes power for the computer. So this is called high side current sensing. So the way this works is this. The ISL6259 is going to measure power at the top of this resistor over here, and then it's going to measure power at the bottom of this resistor over here. And it's going to calculate the difference in voltage, and by calculating the difference in voltage between the top of the resistor that has the charging voltage and the bottom of the resistor with the charging voltage, the ISL6259 is going to come up with how much amperage the actual charger is using, and it's going to turn it on and turn it off accordingly. So if the ISL6259 thinks that this is using more power than it is, or it thinks it's using too much, it's going to tell these transistors, hey, the system is using too much power, turn off the charger and stop sending it to the rest of the system. Now the ISL6259 reads the power from the top and the bottom of this resistor through these 10 ohm resistors over here. So you have this 10 ohm resistor over here going from the top of the current sense resistor to the ISL, and then you have this resistor at the bottom to measure the difference in voltage between the current sensing resistor and the ISL6259. Now what's very, very often happens is one of these 10 ohm resistors gets destroyed because it's a very, very small 1/16 of a watt resistor. It's a small resistor, and it is on the high voltage line of the machine. It is on the, it's directly measuring 18 or 16 volts depending on the charger. So that's one of the things to look at. Now, you may notice something by the battery circuit over here. So this is where the battery attaches to the machine itself. We have something that looks very, very similar. We have these two resistors by this current sensing resistor. So we have another current sensing resistor, R7050, and right by R7050, you have R7051 and R7052. R7051 is at the bottom of R7050, and R7052 is at the top of R7050. And these two resistors report the voltage back to the ISL6259 that the battery is using. So this is how this circuit can tell how much current the battery is using based on the drop of voltage through that resistor. And these are all very, very often the resistors that actually corrode and get fucked up. So now we're going to look on the board view and just take a look and see what values we get for these resistors, because I'm pretty sure that is step one in terms of what is actually corroded. Again, I don't know for sure just yet because all I've done is look at the board. So I know that of these two resistors, R7051 and R7052, that I should be expecting 2.2 ohms for R7051 and 0 ohms for R7052. So I should have 2.2 ohms on this one, and I should have something like, I can't believe I forgot from switching to window, and 0 ohms on that one. So 0 on the left, 2.2 on the right. Let's see what the multimeter has to say. Let's see if the multimeter says anything at all. Let's see if you can actually see the multimeter with the just god-awful lighting in this office. Alright, so left is supposed to be 0, and as you can see, this resistor looks like complete and utter crap. But it is indeed 0. And let's see if it actually makes it all the way to the VIA, all the way to the ISL. So do you make it all the way to the ISL? Like you're supposed to? So this is supposed to be a 0 ohm resistor. So remember, this should make it over here. So the resistor itself, okay, so the resistor itself is actually good. However, its pathway to the ISL 6259 has failed. So you can see what I'm measuring under the microscope. This resistor is 0 ohms over here. Now you'll follow along through this via, and it's supposed to make it over here before it then makes it over here. It never makes it. So the resistor itself is actually good, but the via that is traveling from that resistor to the ISL 6259 is not working. So for R7052, right over here, so this resistor itself is good, but the pathway from here to here is destroyed. It's burned. Now we're going to go over the second resistor. And also, one of the things that you should be doing as you're doing this stuff is actually taking notes. So I'm going to do that because I know that as I'm explaining the process to you, I'm going to forget what does and does not work. So R7052 via from 9 to resistor burned. Now, let's try the second resistor. Now, R7051 is supposed to be 2.2 ohms. That's over here. That's so this is supposed to be 2.2 ohms. It's 2.6, 2.5, 2.4. That's good enough for me. So yeah, that is good enough for rock and roll, as they would say. So now let's see if the actual via going to the chip here again is destroyed. And as you can see here, we have another corroded via because I get OL on the meter. So this to this is just completely, absolutely destroyed. So this probe point is the point at which this via does not work. So that's another wire that we're going to have to draw to make this work. So these are, again, the vias for the current sensing for the battery. Now let's try current sensing for the charger. That's going to be right up here. This is supposed to be 10 ohms, and we get 10 ohms. Now let's try the top one and see what we get. This is also 10 ohms. That's both what the schematic says we're supposed to get. Now let's turn it around to make it a little easier to measure, and let's measure and see if the actual vias to the ISL 6259 are intact or if they are burned out as well. Okay, so when it comes to the charger, that via is looking good. You know. Let's try the other resistor. That via is looking good as well. Now what we should do is check the actual connection between the resistor and the other side. So we have now what I want to do is I want to check the connection between the resistor and the current sense resistor. So right now what I've done is I've checked the resistance between the ISL 6259 and the resistor here that sits between the current sense resistor and the ISL 6259. So I've checked this side, the ISL 6259 to this 10 ohm resistor. Now I want to check from the 10 ohm resistor to the actual current sensing resistor and see what I get. And this is a pain in the ass because this is on the other side of the board. Thank you, Apple. So we do this. This is not exactly fun. Yeah, this is some bullshit right here, actually. Now the next thing I'm going to want to check, because this is also something that commonly goes, is the connection to the battery. So keep in mind, this came in with battery not charging. So while I'm here, while I'm measuring, it only makes sense to check how everything here works. So look over here. Now, to and from battery. Let's talk a little bit about what the entire point of this page is. If you're using the battery is going to take 12 volts and send it over here to where PP bus G3 hot is. PP bus G3 hot is the main 12.6 volt power supply that the entire machine runs off of. Now, let's look at what happens when you have a charger plugged in. If you have a charger plugged in, then the charger is going to be coming through here, and you're going to have these 16 or 18 or 20 volts from whatever knockoff charger you have, voltages depending on what type of charger you're using, coming through here. It's going to come to this transistor. This transistor is going to open and close along with this one. In a sequence, it's going to create a bunch of spikes at 16 or 18 or 20 volts, and that is going to go through this inductor, which is then going to smooth those spikes of voltage into a clean 12.6 volts for the system. So one of the other issues that you have very often, this transistor itself won't actually open because the signal that comes from charger B gate going to the gate of this transistor is not, it is blown. So we're going to check from pin 16 of the ISL 6259 over here. So charger B gate, which is opening the gate of the battery transistor, we're going to check from here and see that this line itself is also good. Because again, I want to fix, I pretty much want to get rid of everything in the circuit that's going to not cause this to not work at once. So let's measure everything at the same time. So Q7055 to pin 16 of U7000. So the gate of Q7055's transistor to pin 16 on the U7000. And again, I say this in many videos, but I'm just going to keep saying it even though it's a very basic thing. When I say transistor, when somebody says MOSFET, bipolar junction transistor, P-channel MOSFET, N-channel MOSFET, all of this stuff is probably confusing as hell and just causing you to go, what the fuck is this thing with all the little arrows and this and blah, blah, blah. Let's make it very simple. This, let me just blow it up. This is a resistor. This is nothing but a resistor. When you see S and D, or in the case of a bipolar junction transistor, when you see C and E for collector and emitter, or S and D for source and drain, those are just two ends of a resistor. And whether or not this is a resistor or a piece of wire depends on what you get at the gate. So this is a resistor whose resistance varies based on this. So pretty much think of this like a brightness control for a resistor. I mean, you can either have a lot of resistance, a little bit of resistance, or none, depending on what you have at the gate. Now you have resistors that are made to either be fully open or fully closed, meaning it's just a wire, or it is fully resisting and off, and you have resistors where it's actually variable, like those that are used in amplifiers for music. But just so you have an idea, when I say transistor, it's pretty much, just think of it like a resistor that can be on or off depending on what you tell it to do. So with that being said, let's check Q7055. Alright, so we have Q7055 over here. We have, let's see, where is our gate? So the gate is going to be pin 4, which is at the right, and then we have to measure that between pin 16 of the ISL. So pin 16 of the ISL is going to be down here. Let's put the multimeter in a mode where it's going to beep to make it easier for me so I don't have to look at it. I'm trying not to stab myself with my multimeter probes. That one is not going to feel good. I should clean that with alcohol, since if I don't clean it with alcohol, I may get some terrible diseases from whatever was on the board that got into my multimeter probes that has now been injected into my bloodstream. Alright, we just clean that with a little bit of alcohol, and it's all set and good and fine. Yeah, it's like I never stabbed myself. Back to work. So we tap the multimeter probes together. Let's tap multimeter probes together. Alright, so we have pin 16 on the U7000, which is already looking burned. Lovely. Oh, not that terrible. Alright, so this to this. Well, that's good. This terribly corroded looking via actually has continuity. Alright, so it looks like all we really have to do here, hopefully, is I'm going to replace that ISL 6259 because it looks like crap. And after I replace the ISL 6259 because I am not confident in it, I am going to run little trace wires from here up to here. and you're going to get to laugh at just how terrible I am at small micro soldering. Alrighty. Also, even though those resistors actually measured fine, I may just replace them because I just don't like looking at ultra corroded shit. And I already know that if the via was blown, that a voltage spike went through them. So if a voltage spike went through, that's not something I really feel like leaving on there. Or I may just wind up tinning them with some nice new solder. Let's see. Because sometimes it's just some oxidation, but sometimes the resistors actually have messed up ends on them. See, that capacitor there I don't have any confidence in because the end of it looks like it's been totally burned off. So that I'm just going to wind up replacing. Poor corroded via. Tweezers would come in handy here, like hot tweezers, I don't mean these. Also, I really do want to grab that. I actually couldn't because this microscope that I use for filming is so much lower than my regular microscope that I can barely fit the damn tweezers in here. Drives me nuts. Alright. I have far too much solder on that center pad, but that is all something that it will be easily removable, as you'll see in the upcoming few seconds. Alrighty. Okay, so I got far too much solder on that center pad. And I'm pretty much pushing it out the side in a nasty fashion. Yep. The thing I like about the chisel tip is that it gets very, very good contact with the bottom of the board. So one of the things I hate about the conical tips that go all around, I don't really know what you're supposed to be touching with them, honestly. I mean, I know that that is the standard iron tip that everybody uses, but I really don't get in many cases what you're actually supposed to be touching with it. The thing that I like about this tip, let's see if I can get some good focus on it in the microscope. You see that? You see how sharp it is at the end? It really makes it easy for touching the bottom of these packages and for getting both the side of the pad of a QFN and also the bottom. There are many other nicer ways to solder QFNs. Maybe one day I'll do a video that makes it look nice and easy, and where I don't run a big solder ball into the work that I just did a second ago and short it terribly. That's what we call not setting a good example. It's not time to clean up just yet because there's still quite a bit of work to be done here. This looks nasty, so I'm taking it off. I don't like when you can't actually tin and make shiny the ends of a component, because it just kind of shows me that it's probably worn to the point where it's either gone or going to be gone about a day after I'm done with it, and then you have the customer coming back to say it doesn't work, same problem as before. So if it looks like crap, I'll give it the benefit of replacing it. That's why it's good to have these dead boards lying around, you understand? You know, I mean, I have so many dead boards. Well, they're not necessarily dead, they're just, you know, I don't know where these things come from, to be honest with you. I just spend 15, 30 bucks on them, and I get all these things that have, these boards that have holes in them, but all the components on them look fine, besides major BGA, which get removed. But it makes it a lot easier to just grab things that you need as you need them. Hey, it looks like my tweezers picked up two things at once here. Once that is soldered, we take that, go away. Now we're going to be running jumper wires, so let's see. My favorite, which is A1226 or A1150 video cable. I cut this open. I do have to find better jumper wire than this someday. The thing is with this jumper wire is that I don't have to order it, and I know it works, and it's right in front of me. So I know it works, it's right in front of me. I don't have to wait for it, so it's right here. So if I need to give instant turnaround to somebody, like most of the people that I deal with, it's right there. Because a lot of the times you guys ask, why do you use this, or why do you have this, or why don't you have that? And it's, well, what I have in front of me works. I already have it. I don't have to order it. I know it works. Like, that is really the reason. I mean, it may not seem like the best reason, and you may look at it like, well, that's not the right thing. You need the right thing. And it's like, the right thing is the thing that I have that already works. I mean, that's the way the real world is, to be honest with you. So let's see how long these jumpers have to be. I should do a little bit of cleaning, since this is going to be a bit of a pain in the ass without cleaning. as the better tip for this. My finer solder is much dirtier than my regular one. Hey, drives me nuts. It is, I really gotta get a different fine solder. This is just soot. It's like somebody's using an ashtray. Okay. Alright, let's cut some jumper wires. So of course the first pad that I actually want to do work on is totally hidden from all light. You'll start to get used to this kind of stuff after a while. It'll just start to become funny to you. Let's try to demagnetize the tweezers a little bit. This is pretty cool. It's a magnetizer and demagnetizer. You'll also get to see how good this 410 magnetizer and demagnetizing thing is. Yeah, as you can tell, this is not exactly the most fun part of my job. I wouldn't necessarily call this the funnest part of my job. The wire went away. Alright, so what I'm going to do is I'm going to take two strands and put them together. So I'm tinning the wire right now, which is me just running solder over it. So that those two strands get tied together and made into one wire. It's also going to help it get soldered to where I want it to go. That's assuming I don't drop it, and assuming that I don't jinx it by saying that. I hate running small jumper wires. This is the bane of my job. Like, figuring it out is fun. Figuring it out, I'm all for. Like, I mean, I have this dream of someday just sitting in the back of the office just, like, telling everybody else what to replace and what to do. Actually doing this stuff is bullshit. Alright. Of course, you're stuck. That is... I can't move my hand properly. Ugh. Patience. Alrighty, not soldered yet. What I'm trying to do now is I'm trying to touch the actual pad of the chip away from the wire to make sure that the wire is actually soldered onto it, not just barely touching it. That's good. Now we go to the next one. This is annoying. I'm not gonna lie, this part of the job sucks. Like, here's the thing, I like solving problems that other people have not solved. That's fun, that's cool. Actually doing this shit, like, this does nothing for me. There is no fun in the arts and crafts part of the job for me. This is just grueling labor. I mean, if you find it fun, then more power to you, but personally, this shit sucks. Nah, oh, nice try. You see what it tried to do there? It tried to be slick. It tried to be slick. Now the thing is, the trace between this resistor and that capacitor is actually intact, so I don't have to be attaching it to both. I can just attach it to one. I'm just doing that for the hell of it, because it makes me feel a little better. Even though I shouldn't really care. But it's just extra. Let's say that via decides to fail for some reason. Whoa. I just shorted solder over a capacitor. If that via decides to fail for whatever reason, the wire is there to back it up. And you never know, it may fail because that via right in front of it failed. So give me that. Okay. Now let's do the beep test. That beeps. Let's see if you beep. I know I shouldn't be touching that because if I touch that I'm going to curse as it comes off, but I just don't feel as confident about that joint as I should if I'm going to be giving this back to a customer and charging money. So I'm going to do something that I tell you not to on a regular basis, which is be a perfectionist. Yeah, this microscope is killing me. I can't hold the iron like this because I only have a 3-inch working distance. This is why some of the time I don't do the videos that I want to do, because I know if I do them with my other equipment that I'll just get it done faster, but I don't have a video up yet on this kind of stuff, so I figured it would be worthwhile. Now let's inspect at an angle. Alright, I'm ready to at least try it. So the problem with this before was that it would not charge a battery. So let's grab a battery and plug it in. Now let's see if this actually works. So as you can see, this is completely unedited, so I have absolutely no idea if this works. So this could go on fire. So before, this had no orange light on the charger, and as you can see, at the end of the video, I have an orange light on the charger. So before, this would never have an orange light. Yeah, one of the things that everybody here has been joking about recently is I get so excited when I see it's charging or I see the fan spin that occasionally I just give it back to my coworkers to reassemble as a fully working board. And there is a place that you can outsource board repairs to where they They literally, like, they see the fan spin and that's it. They're done. I mean, one of the funny ones that I can tell you about. I'm not going to say the name of the place because it would be mean, and they don't really deserve. They don't deserve it. Like, there are places like L2 where I'll happily just bash on them all I want because they have screwed me over and tried to take thousands of dollars and done fucked up business with me with their 30-day warranty on 31-day working reflows. But this place is nice. But the point is, one of these places, a board goes there, and the problem is it doesn't work in an operating system, and it gets sent back to the particular customer in question, and they say, well, it still doesn't work in an operating system. And the board refurbishing house says, oh, well, we actually couldn't get it to boot in OS 10 for some reason, so they tried it in Windows, and it worked, so we sent it back to you. And they charge them for motherboard repair. So I'm going to try to not do that, because I have, like, some of these videos, like, let's say the only issue is no power. I see it turn on, and I pretty much end the video. I really should end the video on actually showing you that it works and showing you that the board has functionality within an operating system, you know. Not get too lazy with it. So let's see that it works inside of an operating system. This is ugh, there's some gunk inside here. Aha. That is okay. Let me watch it. Eh, I'll find some from another machine. So we have a lame 500 gigabyte, 5400 RPM Hitachi drive here, so yeah, I'm not exactly going to time how long this takes to boot up. What I do know is it probably takes more time than I have patience for. So you got the Apple logo. Alright, so let's take a look. So remember, this had a problem of not charging the battery. I'm going to take a walk up front. Alright, so I don't usually edit my videos, but depending on how lazy I was to figure out how my video editing software works, I may or may not have sped it up so that you could see that it was charging. It charges, and it's obviously pretty much just fine. So, that's about it for today. So, let's just go over one more time the topic of the video. The topic of this video was current sensing circuitry, how it works, why you should care, and how to fix it. So let's go back to the monitor here so I can go over that one more time just in case you forgot how this is supposed to work. So, the way current sensing circuitry works is that the chip inside the machine can only sense voltage at different points. So since it cannot sense current, we have to try to figure out how voltage relates to current. So if we put a resistor in between with the charger coming into the machine and where the power actually goes to the rest of the machine, this is called high side current sensing because we are on the high side. Again, this is before power gets created for the machine. We have a resistor that senses how much power the charger is using. The way this resistor does that is there is going to be a small voltage drop between the top of the resistor and the bottom of the resistor as it puts across this 0.02 ohm resistance. Now on each side of the resistor we have another resistor going to the ISL 6259, and this is so the ISL 6259 chip over here can read the voltage at the top of the resistor and at the bottom of the resistor. Now the difference in voltage is going to tell the ISL6259 how much power the machine itself is using. Now the resistors that we actually had to run traces to were not for the charger. We actually had to run traces to the resistors for the battery current sensing. And the battery current sensing is pretty much the exact same thing. So here you have the battery, you have a current sensing resistor over here, and you have a resistor going from the front of the current sensing resistor to the ISL6259 and the back of the current sensing resistor going to the ISL6259. And just to show you again what was wrong here, we had corroded vias that we ran some wires to. So let's just go right back onto the microscope for a second. This will probably get tossed in the ultrasonic to make that look nicer. So pretty much from the current, this is the current sensing resistor. So from the current sensing resistor to these two resistors was fine. But from these two resistors, from the beginning and the end of the current sense resistor to the ISL, those traces were destroyed. So we've run wires, one here and one there, and I stole those wires from an old LCD cable. And that's about that. And as you were able to see, the charger is charging the battery, which means that my circuit works. I'm set, I'm good, and that's about it for today. So one of the lessons that you should learn is that if your battery is not charging, you should look at the current sensing circuitry and not try to attach 120 volts of AC directly to your battery, because I assure you, this thing will blow up and it will be very, very painful for you when it does. So don't do that. Do this, run wires from current sensing circuitry, yes. Run wires from your wall outlet to your battery, no.